Hello and welcome to this video about finite state machines. What you're going to learn in this video is what is meant by a finite state machine. We're going to need to understand that. We're also going to have a look at some of the uses of finite state machines. You're also going to have to draw and interpret simple state transition diagrams. So those are the actual machines themselves. And you're also going to need to be able to draw a state transition table. And that is essentially the machine in a tabular format. And we're also going to look at machines with input and without input as well. So what is a finite state machine? The word machine makes it sound like it's some sort of great mechanical thing, but it actually is not. It's a logical idea, and it's an abstract representation of something that changes from one state to another, right? And it can make that change from one state to another in response to some sort of like condition or event. Now, as you can see on here, look, this is a simple state transition diagram for a locking and opening door, right? So we have got states which are represented as circles, and we've got states for opened, closed, and locked. We show using a directed arrow a transition. So we can see here that we can transition from an opened door to a closed door. And we can transition from a closed door to an open door. And the label on the transition is essentially the condition, right? So in order to move from an opened door to a closed door, we actually need to close the door. To move from a closed door to a locked door, we need to lock the door. So as you can see there, we've actually got a simple state transition diagram that shows our three states, which are opened, closed, and locked. We've got the transitions, which represent the arrows, and they're directed to show what state it's moving from and to. And also we label the transition to say what the condition is, or for example, what the input is. So some of the rules then. One of the fundamental rules for a finite state machine is that the machine can only be in one state at a time. So that it can't be in between states, it can't be on two states at the same time, it can only be in one state, right? And it can change from one state to another in response to an event or condition. So the only way to move from one state to another is through a transition, right? There is no other way to move from one state to another. And the finite state machine is essentially defined by a list of the states that it has and the conditions that can actually be used to move from state to state. And at first, we're only going to look at machines without output. But at the end of this video, we will actually look at machines that actually generate output as well. So we're only going to be looking at machines without output at first. So as an example, a turnstile, and there's a nice picture there to show you what a turnstile is, just in case you don't know. A turnstile is used to control access. So you sometimes see it at railway stations, football grounds, in some hospitality settings as well. And essentially, a turnstile is in two states. It's either locked or it's unlocked. And if, for example, you insert a ticket into your turnstile, then normally a customer is allowed through. But remember, it's only a single customer. So if somebody else tries to push through at the same time, then it will lock, right? So only one person can get through at a time, and you've got to put your ticket in order to allow a customer through. So if you've been to train stations in like London, this is very common. It's less common on train stations up the north, to be honest, but like I said, places where you might have seen this is you might have seen this, say for example, at a football ground. You might have seen it at some sort of hospitality setting, like some cinemas and some sort of like leisure venues use these as well. But one of the key things is that if we push on the arm of the turnstile, it's locked, right? It's the ticket that actually unlocks it, but that only allows one person through. So we can actually show this on a diagram. So this is what we've got. So we've got two states, we've got locked and we've got unlocked. And if we are currently on the locked state, if we keep pushing, we keep on the locked state. So what we've actually got then is this bit here. So if we push, right, all we do is we just retain, we keep on the locked state. But what we can actually do is, if we actually put a ticket in during the lock state, it will cause a transition into our new state. So it will become unlocked, right? So if we put a ticket in, it will become unlocked. And what can happen at this particular state is that the person trying to get through the gate can keep giving us the ticket, right, which will keep it in the unlocked state. But as soon as the person pushes the barrier forward, right, it will then actually go back to be locked again, right? So that is how a turnstile essentially works, is that if the state is locked and we keep pushing, it stays locked. If it is unlocked and we keep giving it a ticket, it stays unlocked. But the thing that makes the transition from state to state is by giving a ticket when it's locked and by pushing the barrier when it's unlocked. So we could actually sort of expand this machine, because one of the things that we're doing at the moment is we're just accepting any ticket. But what happens if we also want to validate the ticket, right? Because you know, there might be the ticket might be valid for certain days, it might be valid for certain journeys. So we could actually have a go at having an extra state, and we're going to call this one ticket inserted. So this is what the extra state is going to look like. So this is a more complicated machine, but essentially it just adds this extra functionality, right? So what we're going to do, look, on here is, if we actually insert the ticket, it's going to go to our new state called ticket inserted, right? And if you notice then, at this point here, if we keep trying to insert the ticket, then it's going to stay on this particular state, right? Now what we're going to have to do then on this state, we're going to determine whether the ticket is valid or not, because if the ticket is valid, we're going to actually unlock the actual, go to the unlock state. But if our ticket is invalid, look, we're actually going to go to our locked state again, right? So this time, putting the ticket in moves us to a new state, and on that state there, we're going to have to perform some sort of logic that's going to determine if the ticket is valid or not. And you can see there, If the ticket's valid, it's going to go to the unlocked state, which means that the person can then push the barrier and that will go back to the locked state again. Right, so that is a sort of an expanded version. So I can imagine what you're thinking right now. You're thinking, why is this important? Finite state machines are used a lot. So for example, robotics, so anything to do with sort of robot control or robot tasks. So things like production line robots, not just not just robotic arms and things like that. It could be any form of robotic process. So for example, even something like a lift essentially operates on a finite state machine. But also things like video games. If you think about any video game that you have played, it probably has at its heart a sort of finite state machine, whereby the game has a state, and it is the game will actually move forward depending on what state it is in. So, for example, you could actually have a menu state when it's the game's at the main menu. You might actually have a playing state when the person's actually playing the game. You might even have like a game over state when the game is finished, and you might even have a leaderboard state where you can actually display the leaderboard. And if you think about while the person's playing, again, you could actually have a finite state machine in the background to control what a person can do. So if a person collects a particular item, it could move them to a different state. Or if a person collides with a certain character, it might move them to another state. So finite state machines are pretty much used quite widely, and it's one of them things whereby it's a very simple idea that you can actually then build upon. And the last one here about this definition of a language, this is something that you actually need to know specifically, is that we can actually use a finite state machine to define what is a valid string within a language, right? So we could actually develop a finite state machine that would actually identify all the valid words within a particular language. We'll look at that in a second. There are two types of finite state machine. The first one we're going to look at has no output, and this is called a finite state automaton. And what we actually have is we have a state that is going to be labeled as the start state, and we're going to have a state which is labeled as the end or the accept state. Now you can have multiple accept states, but obviously you can only have one starting state. And if the automaton can reach a final state, right, it is said to accept the input. So based on the input that you've given it, if it finishes on one of the accept states, then we essentially say that the input is valid, right? So what it's going to do, it's going to start at the initial state, it's going to process the sequence of symbols that you've given it, and it's going to finish up on a state. Hopefully that's going to be the target state. And there are some specific symbols to actually use. I'll show you what those are first. So these are the specific symbols. So a state is obviously a circle. Now the start state is indicated by the arrow, right? So it's the arrow that actually makes it the start state. So you can see here, look, we've actually got this arrow here, look. So that arrow is what makes it the start state. And then we've actually got, look, the next one. So the end state, or the accept state, is actually shown by a circle with an inner circle. So that inner circle is what makes it an accept state. So you can see here that we've got this circle within a circle. So that is the accept state, right? And like before, a transition is going to be just an arrow. The transition is just an arrow. So what we're going to use our finite state automaton for is to actually recognize a language. So it's going to hopefully identify all of the strings that should be accepted by a specific language. So what we're going to do then is we're going to actually create our machine, obviously, and if there is actually a path from the start state to an accept state, and we have processed all the characters that we have been given, and we finish on the accept state, then that particular word is valid within that language. So this is going to show you on the actual diagram here, look. Right, so this is an example. Right, now what you can actually see here, look, is S1 is our start state. So S1 is actually our start state. And S4 there is our accept state. Right? So S4 is our accept state, S1 is our start state. Now what we've got then is we've got 6 bits of text here, bits of string. And we're going to see which ones are valid, right? And what we're going to do is we're going to start at the start state, and we're going to process each character as a transition. So for example, on this first one, we've got A, right? So if we're on the start state, which is S1, right, and we've got an A, we're going to transition to S2. Right, so we're going to transition to S2. So then the next A, right, the next A, that one, we're on S2, and if we provide an A, we're going to essentially stay on S2. So as you can see then on this third A there, right, we're still going to be on S2, right? But if we're on S2, look, and we have a C, we've got that transition there, look, and that's going to allow us to finish on our accept state, right? So what we can definitely say then, what we can say for certain, right, is that that one there is valid. That one is valid, right? So let me just rub these off a second. How do I do that? Using, I said I could just rub them off. Right, so the first one we realized is definitely valid. Right, so the second one then, what we've got is we've actually got the first bit there is a B. So we've got the B. So we started on S1, so the B there, look, is going to move us on to S3. Right, now interestingly here, look, our next character is an A, but on S3 there is no root from S3 that actually has an A on it, because from S3 the only thing that we can accept is a D. That's the only thing that we can accept. So we know for certain then, so we know for absolute certain that that one is not valid. That one is not valid. All right, so if we just rub these off. So the third one then, so we're going to start on our accept state, and our first value is an A. So we're starting there. We've got an A, so we're actually on S2. Now the next character is a D, and if you notice, look, that's there, so that transition means we're actually going to go back onto S1. Okay, and then the next character is an A, so again we've got an A there, and we're gonna go onto S2. So our next character is a D, so that means that we are gonna get on that transition, and then we're gonna be back on S1. So our next character is a B, so that's gonna go on this transition, and we're gonna be on S3. And then our final character, look, is a D, and that's going to allow us to use that transition, and we're going to finish on S4. So what we can say for certain is that one is valid. That is a really bad, sorry, that is a really bad tick. Let me try that again. Yeah, so we can say that that this one is definitely valid. Right, so that one is definitely valid. So let me rub these out a sec. And let's get rid of that one, let's get rid of that one, let's get rid of that one, let's get rid of that one. Right, so this fourth one then. So what we've got then is we've got an A. So we started on S1. We've got a transition for an A, and that's going to move us to S2. And then our second character is a C, and on S2, look, if we have a C, we get to S4. So again, we know for certain that that one is valid. That one's definitely valid as well. All right, let me just rub them out. And the next one then, what we've got is, so we start with a B. All right, so that means then that we're going to start on S1. We've got a B, so we're going to transition to S3. Right, now our next character is a D, and as you can see here, look, we have got a transition from D, and we are now on our accept state. Now the problem is though, right, is that next, look, we've got an A, right? There is no transition from S4 for an A. So if there's no root, same as in the second one, it is definitely not valid. So again, we can say for certain that that one is wrong, right? So that one definitely is invalid, definitely. So if I clear them off, and then this second one, the last one we've got, sorry, is this one. So we're going to start on S1 again, and we've got a B, and that allows us to use that transition. So we're now on S3. And then our final character is a D, and we've got a transition there for D, look, and that gets us on our accept state of S4. So we know for certain then that that one is valid, right? So that's how you can use a finite state machine to actually check which are valid within a particular language. Right, so the first thing for you to do then is using the Paper 1 Year 1 workbook. If you have a look in the contents page, there is a section for finite state machines. It is the very, very, very last section. If you have a look, if you find that section, there is the first thing you'll see after the aims sheet is task 1. So have a go at the questions in task 1. You might want to pause this video here and then come back to it once you're done. Right, so we've looked so far at state transition diagrams, but we also need to know how we can represent these within a table called a state transition table. And as you can see from this little finite state machine below, it accepts inputs of A and B, and the table actually shows us how we can actually represent this as a in a diagrammatic format. So as you can see here, look, it's actually got what the current state is. If the input is an A, it's going to move to S1, so it's going to stay on S1. And if the input is a B, it's going to move to S2. And as you can see there, that is pretty much what we've got here. Look, so S1, if you've got an A, it's going to stay on S1. If you've got a B, it's actually going to go to S2. Right, so that's pretty much exactly what it says on the diagram. And then the second one then is if we're on S2 and we've got an input of an A, we're going to move to S1. So if we're on S2, look, and we've got an input of an A, we're going to move to S1. So that is accurate. And if we're on S2 and we've got an input of a B, then we're going to stay on S2. So that is how we could actually create a state transition table. Now, an alternative layout then, which might be a little bit better, is to actually use this table instead. So if we've actually got S1 and we've got an input of an A, it's going to stay on S1, right? If we're currently on S1 and we've got an input of a B, then we're going to move to S2. And if we're on S2 and we've got an input of an A, we're going to move to S1. And if we're on S2 and we've got an input of a B, we're going to stay on S2. Now, I think this is a better method of doing a state transition table, because your machine might have many different inputs. So it's not probably a good idea to use the previous example. The other thing you could actually do as well is it would also be a good idea to maybe label somehow what is the start state and what is the accept state, because none of these methods for state transition tables actually have a way of indicating what the accept or the start state is. But all the questions you're going to do later, as you can see from the exam board, that's never really an issue. They ignore that fact. So that's a better way of setting out a state transition table, because it allows us to have many inputs. So if say, for example, S1 wanted to have 3 inputs, we could do that. If S2 only wanted 2, that would still work as well. So it's probably a better method. So this is an example that we'll have a go at. We have got, this is our machine. So if we're on S1 and we input a 0, we're going to stay on S1. So if you notice, that is that transition there. If we're on S1 and we input a 1, we're going to move to S2, which is that transition there. So if we are on, if we're on S2 and we input a 0, we're going to actually go to S3, right? If we are on S2 and we input a 1, we're going to stay on S1. Okay. So S3 then. So if I input as a 0, we're going to actually move, whoops, to S1. That is really not a good S, but there you go. It's a little bit more readable. And if we have an input of a 1, we're going to actually move to S2. Right. So that's how we could easily fill out that particular transition table. And then the last bit, which of these strings are accepted? So remember, the accept state on accept state on here is S1, and the start state is also S1. So what we're going to do then is the 0 there then. So that 0 is going to stay on S1. So the next 0 is going to mean that we're also staying on S1 as well. So we're going to stay on S1. The 1 is going to use this transition onto S2. The next 0 is going to use this transition from S2 to S3. And then the final 0 there is going to get us from S3 using that one there and using the S1. So we've actually had a route using 0, 0, 1, 0, 0 from the start state to the accept state. So what we can say for certain then is that is correct. Right, so the next one, we just rub these out. So the next one then, what we've actually got, we have got a 1 as the first one there, look. So we're going to move from S1 to S2 using that one. So we have got a 0, and that's going to use this transition here to get onto S3, and then the last 0 there, the last 0 is going to use that transition, and we're going to get back to S1. Right, so we can say that that one is correct. That was definitely correct as well. Right. So if we have a look at the next one, let me just rub these out. So if we have a look at the next one, so if we've got a 0, then we're going to stay on S1. So S1 and the 0, we're going to stay. So the next one then is a 1. So that's going to make us move from S1 using that transition there and be on S2. Okay. So the next 0 there then is going to use this transition, and we're going to end up on S3. And then this final one here, the final one, that is going to use this transition here, and we are going to still be on S2. We're going to be on S2, right? And we've got no more input. Right. So one of the things that we can say for certain then is that this one is not correct. That one is definitely incorrect. So the final one of these then. So the final one of these, we can see that for the 0, we are going to be on S1, and we're going to stay on S1. So the 1 is going to move us from S1 using that transition onto S2. The 0 there is going to move us on this transition to S3, and then the 0 there is going to move us on this transition back onto S1, and then these last two zeros are essentially going to use this transition again. So we can say for certain that that one is also valid. Right? So we worked out again which of these are valid strings within this language. So that's how we can define a finite state machine to do that, and obviously that's the state transition table that we actually needed for this as well. Right, so if you go back into the paper 1 year 1 workbook, and again it's under finite state machines on the contents page, which is, I think it's the very last one. So you've done the questions that are labeled task 1. So next we want to have a go at doing task 2. That's going to go through you know, the bit we've just done about transition tables and the like. After you've completed that, there are more questions. Funnily enough, they're actually called finite state machine questions and more finite state machine questions. But on that last section, can you only do questions 1 to 3? Right, so have a go at trying to do that. So you might want to pause the video here, and the reason why you only need to do 1 to 3 is the questions after 3 are about machines with output, which is what we're going to look at next. So if you want to pause it here, you can get those done and you can start it when you're ready. So everything that we've considered so far have been finite state machines that actually have no output, right? But we can have the final type of finite state machine, because I said there was 2. There was the finite state machine automaton, and the other one is a machine with outputs, and it's actually called a Mealy machine. I think it's after the person that devised them. I can't remember his name, to be honest. And the only difference is every transition, right, is labeled differently, right? What it has is you'll see on the transition, right, it will have, first of all, what the input is for that transition, right? So it'll have what the input is for that transition, and then after some sort of clear divider, it will then actually have the output that transition generates, right? So when you come to look at these, machines in a minute, just remember that the transition is labeled with the input followed by the output, right? So we've got an example, I think. So this is an example of a Mealy machine, or a finite state machine with outputs. And one of the things that we need to remember then is that the transitions are labeled with what the input value is and what the output value is, right? So again, on this one, we have got an input of a 1, and that will generate us an output of a 0. So remember, these transitions are labeled with the input value followed by the output value. And what we're going to actually have a go at is we're going to have a look at this particular input. So we're going to have a look at this particular input, and we're going to generate essentially our output. All right, so we're going to go through it bit by bit. So what we've got then is we have got a start state. So that's where we're starting, right? And my first value there, look, is a 0. So we're going to be on S0, and we're going to actually use that input there. And that's going to generate us an output there, which is going to be that 0. So that's the 0 that's going to be created by that one. And now we're going to be on S2. That's where we're going to be. So this next 0 there is essentially going to give us this transition. It's going to output us a 0, and it's going to be the second 0 there. Okay. So our next input then is actually a 1. Right, so our next input is a 1. So we're going to use this transition, and our output is going to be a 0. That's going to be our output. So it's going to be that 0 there. Okay, but we're now on S1. We're now on S1. Okay, so our next input value, right, is this 1, right? And that is going to give us that particular input. That's the output we're going to actually put, and that's why we have got that one there, right? So we're now on S1 still, right? So our next input is a 0. Oh, let me just rub that out. I've gone over that other 0 there. Right. So our next input is that 0, which is going to use this transition, and our output is a 1, and that is my output there. Look, right, and I'm now on S2. Okay, so on S2 then, if I've got a 0, right, I'm going to use this one again. So it's going to be that one again, and it's going to produce me an output of 0, which is that one. And then I am still on S2, all right, and my next input is a 1. So that's going to use this transition again. Going to use this transition again, and my output is a 0. So that's going to give me that 0. And then the final bit is we're currently on S1, right? My input is a 0. I'm going to use that transition there. My output is a 1, and it's going to give me that transition there. So as you can see then, that using this machine with this as an input, using that as an input, we will get that as an output. So a Mealer machine, a finite state machine with outputs, can actually do processing. So now you know what a Mealer machine is, or a finite state machine with outputs. There is some sections for you to actually complete. We want to finish off the last set of questions because before you did questions 1 to 3. So question 4 onwards are about finite state machines with outputs. And the final thing is I have emailed you, and also on Teams, I'll actually attach an extra set of questions, which are all of the exam questions that they've had on finite state machines. And if you want to have a go at doing those, and then that's pretty much the topic completed. It is important to have a go at doing this topic, because the next topic we're going to cover is actually called Turing machines, and Turing machines use finite state machines as one of its components. So thank you for watching this video, and hopefully you've learned a lot about finite state machines. If you've got any questions, I'm going to be around on Teams, and also you could email me, right? But thank you very much, and goodbye.